Okay, YouTube, in this video we're going to look at sketching graphs of functions. Now that we've kind of got an idea of how we can do this by making a table, looking at x and y intercepts, but also checking for symmetry here. And so using all kind of three of those things, we should get a really good idea what this graph would look like before we even sketch it, and then also be able to sketch it. So taking a look at this example, let's go ahead and take a look at what we have here for our function. We have y equals the absolute value of x minus 1 there. And so I don't know if you recall what your absolute value graphs look like here, but we'll get a good picture here after we check for these three things. We'll start with the x-intercept. Remember that for an x-intercept, what you're doing is you're substituting in 0 for y. And also another thing I want to do here is this. For people who don't want to just kind of write this here, x-intercept, we could write a little table here. But we could table these values. We're going to plug in 0 for y to find our x-intercept here. And so because this is an absolute value equation, remember that we have to now rewrite this two different ways. We have x minus 1 equals 0 and x minus 1 equals negative 0, which I understand makes no sense. But because it's set equal to 0, it's not going to affect it very much here. In either case, we get x equals 1. But often, we'll get two different answers with absolute value. So our x-intercept is 1. We know that it hits at an x value of 1. Now, in terms of the y-intercept, plugging in 0 for x, we would get something that looks like this here. We have y equals the absolute value of 0 minus 1, which is y equals the absolute value of a negative 1, which, as you might recall, is a positive 1. So it also hits at a y value of positive 1. So the neat thing about this is we kind of already have two values for our graph here. And I'm going to write these over here as well. They both have an x and y-intercept of positive 1. Now, in terms of symmetry, we have to check for all three types of symmetry here. I would say that x-axis symmetry, we plug in a negative y value. So we say plug in a negative y into our equation here. I suppose that we could see that if we were to take both sides times a negative 1 in order to make our y value positive again, what we get is the negative absolute value of x minus 1, which is not the same thing as what we started with this expression here. And so it doesn't have x-axis symmetry. Let's talk about y-axis symmetry here. We'll plug in a negative x. And so something interesting happens here I want you all to see. But we plug in a negative x on the inside of an absolute value here. And so one might think, hey, it just turns all this stuff positive in here, and this is the same as x plus 1. But when you have an expression like this, negative x minus 1, we're kind of looking at this as one solid number here. And if there were a negative out in front of it, I would suggest that, yes, you could actually do that. But right now, there is not. And so what I'm going to say here is that y equals the absolute value of negative x minus 1 is our expression. We're going to leave it this way, but it is not the same as what we started with here. And so it doesn't have y-axis symmetry either. So let's check for origin symmetry, which of course we would plug in a negative y and a negative x. So negative y in for our y, a negative x in for our x. And we could see that we would really, by multiplying both sides times a negative 1 here, what we're going to end up with is a positive y equals a negative absolute value of a negative x minus 1, which still is not the same thing as what we started with. So this graph does not have any types of symmetry that would help us sketch this in terms of being flipped over the x or the y-axis or both. But what I do know is that I also know it can't have symmetry. So when I make my table here, the interesting thing is, let's see, x and y. I already have a couple of points that go on this here. At least in terms of my x values, I have 0 and 1. So I'm going to put 0 here in the middle. I'm going to put 1 here. So when x was 0, I have a y value of 1. And when x is 1, I have a y value of 0. In terms of some other points, maybe we'll go 2 and 3, and we could also work backwards here like a negative 1, a negative 2, negative 3. So plugging these in, let's go ahead and substitute a few of these in here. If I plug in a 2, we would have y equals the absolute value of, and we'll just go ahead and list these in here. If I were to put in a 2 right here, we'd have 2 minus 1, which is 1, and the absolute value of 1 is, well, 1. So we'll certainly get a 1 here. If I plug in a 3, we would get a 3 minus 1, which is 2, and the absolute value of 2 is 2. And then going backwards here, if we plug in a negative 1 minus 1 is a negative 2, but the interesting thing is its absolute value. So this becomes a positive 2. A negative 2 substituted in would become a negative. Make this expression inside the absolute value negative 3. And so we get a positive 3, and this is actually going to be a positive 4. So what we get here is this graph that as we graph these points here, 2, 1, I'll go right 2 up 1, right 3 up 2. And as I go left here, negative 1 was at a height of 2 as well. And negative 2 is at a height of 3, and negative 3 is a height of 4. We get something that looks like this. And so as we imagine this here, we could see that this absolute value graph, of course, is a V. We look at these as V's. But we can go ahead and connect these dots here because there do not exist any x values for which this y value wouldn't exist. So all x values are in this domain. But let's recall as we sketch this here, we do want to label our graph here. And so these, just to to note this here, I want to make sure you note this here, are the solutions of this equation, basically. Cheers.